joining us. I'm very much happy to introduce Dr. Mohamed Ali. He's an associate professor in the Department of Electrical and Computer Engineering at Cal Poly Pomona, CPP, and also the director of the Reconfigurable Space Computing Laboratory. So, floor is yours, please.
Thank you. So, thanks so much for the kind invitations. I would like to talk today about, the idea of building a swarm or umbrella of drones that will be acting as a massive edge computing cluster for accelerating AI application. And the title is Scalable Edge Computing for Autonomous UVs, Kubernetes-Based Deployment for the Real-Time AI Processing. This is a part of a US Navy grant we received like a year ago. The grant's supposed to be for 3 years for adding natural language processing to the drones, so the drones will be chatting to each other using BERT models. So pretty much, why we need a scalable edge computing for autonomous UVs. And, pretty much you can see that I use GPT for creating the pictures in the side because, there is nothing like that already exists. So for the real world challenges, as all of you guys heard about what happened in California, the disasters about the wildfires and all these things, it's really hard, to sacrifice humans and, the firefighters to send them in a really dangerous spots or even in a war zone or like, diseased area, like, full of COVID, whatever. So pretty much, you need a really full equipped drones, but the problem with drones is really constrained by the battery lifetime. And every single screw on the drone is considered a payload because it has to fight the gravity, so it will be flying at a high power and all of these things, right? So autonomous UV real-time AI processing is an obstacle of the detection and decision making. Most likely people, what they do a very naive computation on the drones, but then, if they would like to do further processing, they send it to the cloud. And then, they will be hit into the fact that, the latency. And then, you have to go into the 5G or 6G or all of these communication protocols to decrease the problem of the latency. And then, of course, the security and scalability. One of the problem also, when we have a bunch of drones scattered in the air is how when they will be talking to each other, are they going to be secure or not? And if you add the security element here, then you're going to add more latency. And indeed, it will be more energy to be consumed and all of these things, which is affecting in the battery lifetime. And if these drones are attacked by the quantum machines, then what are you going to do? You have to have something that it will stop the threats of the Shor algorithm and the Grover algorithm, which is used for the prime number factorizations. And pretty much you have to be able to processing something called post-quantum crypto, which is based on the mathematical primitive is called learning with error. And, the most famous National Institute of Standard and Technology standard is called Crystal Kaiba. And of course, in the top of that, what will gain if we build such a kind of infrastructure that will allow us to run all of those guys in the background and the battery will not be affected? Definitely, we'll be enhancing the autonomy, we'll be improving the security, and we'll be able to have a very strong product that it will be taking care of the disaster response, surveillance, and defense applications. Now, what challenges we have to break it down? So you will find out that, real time. When I say real time, you need a camera, and this camera will be streaming videos. And you don't need to be streaming videos. Actually, you need to select what you need from the video. And pretty much, the solution came from computer vision guys using YOLO, right? So the YOLO model, 1 to the 8 versions, we need to figure out which one will be the best for the drones and, which one will be best for edge computing, which one will be best for the cloud, and how we're going to be making this orchestrating correctly. And definitely, we have to be hit with the latency, scalability. How are we going to be, let's say that, I have 10 drones in the air, and then, they are sharing all of their resources at the same time, but then for a reason or other, one of the battery already died, right? Then, are we going to be offloading the workload that it was assigned for these drones, or are we going to start from scratch to overcome the problem that, one of the drones were participating in the computation where is dead? Then, the security, we already mentioned that. But pretty much, if I involve security in this talk, we'll finish in 4 hours. So, pretty much we'll push it into the AI first. So, my goal here is to enhance the real-time performance which is basically adding, orchestrating some computing on the drones, and having NLP, as I mentioned, as a US Navy grant that I've been working with, and of course adding computer versions. And the final version of this project, it will be talking to the drone and say, go to the top of the building, and then the drones will reply back and say which building. So, we need the drones to come back and forth, instead of using controllers, it will be speaking to me like a human. So that means there is an element also of having audio to the text conversion. And we'll be talking about that. We have a paper recently got accepted in military conferences called NAML, Naval Machine Learning, in San Diego. It will be presented in end of February. And then, how we be orchestrating, there is Docker Swarm, there is NAMD, there is Kubernetes. Which version of Kubernetes will be the best? We're going to be talking about that. Security, we'll keep it at the moment. Okay, so we need to understand what drones, right? So when I say drones, it's many things. It could be quadcopter, it could be fixed wings, it could be many things, right? Which most sophisticated and hard to deal with? Quadcopter. So let's start with the difficult one. So when I would like to build, when I would like to cook a lasagna, so what I'm gonna do, I'm gonna go bring the list of the parts, or the ingredient from the market, like Walmart or whatever, and I start putting and sorting in an order, right? So if I would like to build a drone, and this drone to be open source, there is no open source drone. So you have to build something that it will be easy for you as a testbed to build such a kind of experiment. So you need a kind of EDF, which is this ducted fan in case of like pushing in a high altitude, but you will be sacrificing a lot of energy, or you will use a propeller based and brushless motors. And pretty much when I say brushless motors, you need an ESC, which stands for electronic speed controller, that will be controlled by the flight controller. And this flight controller is a bunch of flight controller here, as you can see in the right side of the slide, which is like, it has a CPU and it have a runtime operating systems, and it could be running a flight controllers like, F prime, which is be directed by Jet Proportional Lab, or it could be using PX4 and Abdo Pilot, which is pretty much, a state-of-the-art flight controller for drones. Or in the top of that, you need sensors to gather the information to keep the drones alive. So you need a GPS to tell you the coordinates and the position. You need an IMU, and this IMU, it could be 9-axis or 3-axis or 6-axis. And when I say 9-axis, that means it can be going into the gimbal positions. It could be in a compass, and it could be in also, geometrical position for the drones as well. And on the top of that, you need communications. Are you going to be communicating in long distance? You're going to be using LoRa, or you're going to be using a different telemetry. And of course, telemetry in the United States, it's 915 megahertz. The other one here in Europe is 400-ish megahertz. So, how are you going to be switching from one to the others? And definitely you need a battery orchestrating the power distribution on the drones. And this called, power distribution boards, and how are you going to be act with that? So if you got all of these ingredients in your hand, you already built the first part. And of course, you need a 3D printer to build the drones that it will be lifting such a kind of equipment that will have Kubernetes. Okay, so what is the data flow here? From the sensor to the action. So pretty much you need the sensors to get information sent to the flight controller. Flight controller would be running a bunch of filters like PID, Kalman filters to keep the drones in the air without a problem. So let's say I'm a quadcopter and I would like to go from the ground, take off to a certain altitude. So what I need to do, I need to spin the propellers by high RPM, all of them equivalent in the same RPM at the same time, to go in the top in a certain level when the weight of the drones will be higher than, the weight of the push of the thrust of the four motors higher than the weight of the drones. Once you get into a certain point and the thrust exactly the same as the weight of the drones, you will be hovering. If the thrust is less than the weight of the drone, you will start landing and the gravity will take you down. If the thrust is higher than the weight of the drone, you will keep going up. Now, if I would like to tilt to go to the right and the left, it's really quite simple. So and here in this case, those two motors, if I spin faster than those two motors, I will move forward to this direction. But if I would like to move to this direction, those two motors will be faster than those, and I will just move forward like this way, and this direction and that directions. So pretty much, you can see here geometrical representations about, the yaw and pitch and roll, and those three coordinates, you need to do something that's called tuning and how to make auto-tuning in the autonomous systems as well. And then, the second in the process after inputting is going to be processing, which is collecting data from the YOLO. So that means you have a high resolution camera and you have to calculate the battery lifetime and the power budget that will be consumed using this sensors. Then, of course, running BERT, and we're going to be talking about how it's be done. And then the output going to be the action, which is moving the drones or even deploying something. It could be a rocket. It could be sending some kit for patients that you need, AKG or, something, going to help until, they will be sending the ambulance for taking them or, just lift them by using helicopters. Now, what is this equipment? Edge computing. So, we need it to be low latency, autonomy, and reliability. And we already talked about the sensors and the flight controllers, and we talked about the actuators in robotics, which is basically the motors. Now, let's go for the edge computing. So edge computing versus cloud computing, for such a kind of processing, you have to think about the latency, you have to think about the autonomy, reliability, and energy efficiency. You will find out from the graphic representation in front of you by 2D graph with the key metrics and performance score. You will find out let's go for the edge, don't go for the cloud. The cloud gonna be a big mess unless we will tell you when the cloud will be a part of this game. And for the cloud, it's going to be more centralized and processing, high latency and limited in autonomy as well. Okay, now what pieces exist in the market we can use to build such a kind of edge computing for the drones? So there's something that's called Cluster Hat 2.5. What is this? It's literally a hat going in a Raspberry Pi, and then it allows you with a USB protocols to sort a 4-arm Raspberry Pi PZW, which is 0, and it has a wireless. And then, those can be running, but it's limited in a power. It doesn't have a power of computing as if you are using, for instance, GPUs, or you are using sophisticated compute modules, or even, Rockchip RISC-V architecture. The other one, which is called DiskPi Super 6C, and it's suitable for the medium scale deployment because it's allow you for every single compute module that you add in the back end, you can have NVMe SSD. It can go up to 3 or to 4, I think, terabyte of data. And the Turing Pi itself, this is actually what we're going to be, end of the day, using it for the drones. It's a board, it has a network switch, is uncontrolled, and it has 4 lanes that allow you to put Jetson Nano, Jetson Orion, or Jetson Zephyr, or, TRK1, which is actually a chip created by the company created the Turing Pi, but it can be using Rockchip. And then, it can be combination between Jetson Nano, and it can be Orion and, TRK, or even Compute Module 4. Then, Bitscope, it's a company located in Australia, and they already published a paper like 4 or 5 years ago in supercomputing about orchestrating 100 Raspberry Pi node with a massive storage that it can be running Kubernetes, all of them together, to do like a kind of computation similar to the supercomputer, but in a smaller scale. So they study the architecture before they move forward to the actual supercomputer implementation and execution. And, all of this we have in the reconfigurable space computing lab. We tested all of them. We tested the energy, and even we already have a thermal camera looking into every single piece onto it, so you can see the IC aging, whether that it will be aged if we use it massively for a long time, or it would be just operating for a long time enough, and that would be the fair enough. Now, we have a very nice roadmap having the cluster type from the Bitscope cluster module, and this one is a 48 node at a time of Raspberry Pi, Turing Pi, which is 2.5 or 2.0, DiskPi Super 6C, and Cluster Hat. If you would like to look into the parameters of the comparison between of them, you're talking about capacity, suitability, processing power, and the primary application. You will find out the Bitscope is more into 48, 96, 128 Raspberry Pi running in the boards. It's a large-scale deployment for education and research industrial application. Processing of power, it's a really high-power distributed system. And then, primary application, data processing and simulation, and also for research perspectives. That's why we are using for the NLP process. Turing Pi is actually a combination between Jetson, as I mentioned, and Raspberry Pi. It can be running machine learning, edge computing, and Kubernetes we mentioned before. And of course, it can be running real-time analytical for the massive data processing. And it could be also used for IoT application. And I can consider drones in this case as IoT application. Now, for the Disk Pi Super 6, it can be running up to 6 Raspberry Pi Compute Module 4. It could be actually for suitability small to the medium scale cluster, and you can build a NAS and even cloud applications using the Disk Pi Super 6. And the processing power depends on the EMC, the flash of the Compute Module 4. I can tell you the application, and pretty much if you would like to make a NIC or network storage, go ahead for the Disk Pi Super 6. Cluster hat is really tiny kid. It could be used for little network for couple of terabytes, orchestrating it, limited for the small scale, and it can be used for the education and the network setup processing. Okay, this is the graphical representation of every single piece. So, Mitscope, it's, as you can see in front of you, it's a big piece of ship. So if you would like and tell me there's going to be a drone in the air, so you're actually looking for a heavy lifting motors. And, there's heavy lifting motors. I can make it actually fly, and it could be used for military application. For the Disk Pi Super 6C, these two pictures nearby to each other is actually back to the back. So the front is the Compute Module 4. In the back, every single node in front of you of Compute Module 4, it has its own NVMe SSD. And I mentioned it could be up to the 4 terabyte of data storage. Jetson Nano, everybody knows Jetson Nano. Cluster hat, and this is basically the one I told you about. It could be Raspberry Pi ZW going in 4 nodes in parallel, and the Turing Pi, as you can see in the side. Now, we're going to dive into the criteria of selection of what we're going to be using for the drones. Processing power, scalability, and energy efficiency, and compatibility to the Kubernetes. At the end of the day, Kubernetes, it's 2 different types of Kubernetes. We have K3S and K8S. K8S is more into the high performance. It has a graphical representation. It's too fancy. K3S is more into the seamless. You're going to be just accessing through the terminal. So pretty much, you can know the answer. K3S will be the one we're going to play with in this experiment. And the portability, definitely, portability, Turing Pi will be a good candidate for this. And there is a graphical representation here in front of you telling you which one would be the best for our case. And you can see that the purple big area is coming from the Turing Pi, telling me that its scalability is great, energy efficiency, and Kubernetes compatibility, portability, and the power of processing is really the best based on the spectrum of the LiPo batteries used for the drones. And that's why, we move forward through the Turing Pi. Now, let's dive more in Turing Pi. So the Turing Pi, it has 1 giga of the LE2 managed switch. It has a baseboard management controller, BMC, and it has 1 gigabyte of ports. It has 2 mini PCIe slots. It has DSI. It has a bunch of USB 3 and 2. It has an RTC battery slot, so, for the timing and, for atomic timing. And it's actually the energy efficiency. If you run 4 GPUs, fully running in parallel, and all the capacity will be used, it's going to be less 80 watt. And then it could be used in VLAN support. It can have HDMI. It has actually around 40-pin GPIO for debugging systems. It has SIM slot, and it could be actually used for power supply 24-pin ATX, and it has a mix of multiple compute modules, as I mentioned. Now, let's look into the compute module compatible for this Turing Pi. You'll find for general computing, you have the RK1, which is their own chip based on the ROC chip RISC-V. And the CPU, as you can see the number, and it has an 8-core CPU and the RAM up to 62, which is making very great even for the K8S. And then Raspberry Pi is the baby, so it has just 8, which is really good for the K3S. Now, if you are targeting machine learning, so this is all of the good candidates that can be using all of the 4 nodes actually in parallel. So just Orion, all of the stories about the teraflops from the 100 up to the 0.12, and the RAM you already have in the side from 16 to the 8 and 4 and 4. So, I'm not going to come and tell you that. I'm sure that you know it. So pretty much, something here is more interesting. So they developed a benchmark. It's called Geekbench 5. And, this Geekbench 5, in the next slide, it will tell you what is inside it. So pretty much, they make a comparison between Turing RK1 single core to multi-core versus the Compute Module 4 and Orion NX 8 gig. Look at the numbers. In the multi-core score, they are not really far from the Jetson Orion. And don't forget, this is CPU based. That means, energy consumption, it's way less than the energy consumption of the Jetson, because end of that is GPU, right? For the compute module, it's out of the whole entire game, because end of the game, the score is really quite low for the multi-core score and the single core score. So that's really quite interesting. If you would like to play the game of running drones based on your budget, you can jump between Turing RK1 or Jetson Orion NX. And this is basically the rock chip that they already have. And RSCL, we are building our own chip now, which is combination of FPGA and FPAA, which is field programmable analog array. So we combine FPGA and FPA in the same board, and the component of field programmable analog array will be working with the signal processing applications, while the FPGA will do all of the data processing and data analysis part. And the FPA chip we are using is from a company located in London. It's called El-Hadedy. And I think there is a professor in Georgia Tech. She was the lead, and she's still the lead in the field programmable analog array. Her name is Jennifer Hessler. So she's doing a lot about, massively increasing the resources on the field programmable analog array to be neck to neck to the FPGA resources. As you know about, million of lookup table now, and we have HPM and all these extra things. Now, what is Geekbench that, they are talking about? It's a bunch of kernels. Some of them is targeting the CPU and some of them is targeting GPUs. So we'll find the CPU from security AES using the CVC mode of the XTS, image processing like Gaussian blur, histogram equalizations, GPAC compression, and GPAC, we are talking about DCT based and, wavelet based. And then, data compression, LZMA, and then, physics simulation in-body, and then, the text processing, HTML5, speech recognition, and that's why we are using that thing, for the converting even, to the text. Pathfinding and machine learning inference for the neural network inferences, the CPU, while you already have listed in the last 5 locations in the table for the GPU from the deep learning and test of the neural network inference performance. Still image processing is running in the CPU and GPU, and the particle physics, simulations of the Monte Carlo simulations, object detections, YOLO in that case, and FFT, state of the art for any benchmarks. Now, the orchestration. So, if we say orchestrations, in the early of this presentation, I was saying that, we are aware there is orchestration because we already have a bunch of nodes in front of us and we need to orchestrate them. We're not going to be manually feeding them. And then if something wrong happens, we have to manually take it out and build all these things. So we have Docker Swarm, we have Kubernetes, we have Nomad, and we have Apache methods and, Apache Flink and all this crazy things. Scalability, you will find out that, Kuber and Nomad is actually the high complexity. You will find that, Docker Swarm is really low, but it's completely in a fault tolerance. It's basic. And, you're flying drone, maybe some ultraviolet will hit it. So, fault tolerance is not really the best. So pretty much you have to go in advance. That's why Kubernetes and Nomad, and then, Apache Moses, it will be our choices. So, resources allocation, the greatest part about Kubernetes is dynamic, so that's why we selected, and pretty much use case is going to be the UVs as we mentioned. And, I'm not going to go in details about how Kubernetes work because, you already have a control plane and you're already actually sending pods, and this pod, it will be based on the resources allocation. It will be distributed between to the others, right? And now, integrating AI models from NLP and YOLO into that Turing Pi, they're going to be on the drones, right? So first, NLP. So what is NLP? Natural language processing. End of the day, we need it for what? Land at the nearest safe spot. I'm going to be panicked while I have the controlling in my hand. So end of the day, I can just fake, right? And say, just land in safe area. And that's it. Communication got broken. Then, it remembers somewhere in the buffer and it will just land safely. benefits, humans can interact, especially like in panic situations. And then, YOLO, it will at least will be my advanced eye looking for certain location, especially, one of the biggest problem we have in California in the wildfires, the Edison, which is the distribution electricity company, they have to shut down the electricity in areas, in a certain area, like disaster areas, because, once explosion happen nearby the gas sources, end of the day, gonna be more fire, right? So, if there is bolt in the hot line is already broken, you need a drones that would just go around and just like see even that tiny bird on the thing, the little bolt, right? And it'll just say that, shut down this line.
About limited minutes.
No, it's written back.
Is it back again?
Yeah.
Yeah, we have 22 participants. I think we're back. Can you confirm we're back online?
Yes, we're back
Okay,
now.
thanks for that. So you will have to share the screen again, I think.
Oh, I'm sorry about that. Okay. Okay, no need to go back to this. Share screen. Okay, so there is multiple versions. There is 110 million parameters. There is 340 million parameters. The one at the moment we are using in our experiment is 110 parameters. What we did, we just get pre-trained models, and we added 2 extra layers here, which is basically the CLS input, and then we put it like the coordinates, the position, the altitude, orientations, and the biggest problem we ever faced, we don't have data to train. So we created data, we brought some model somewhere else, and we just say, give us whatever numbers. Until the Navy said, we're gonna sign with them some clearance documents, and they give us some data, but then I cannot share it. So, it's like for actual missions and stuff. Is it stuck or what? Okay, this is my server. So that was my Bitcoin miners when I was really bored during the pandemic. So I give it to them in my lab. It's up here, as you can see. It looks really Bitcoin, and we have a balloon we're playing. But then, did you see the one in the rack inside? That's Bitscope, basically the one I was telling you. At the moment, we have a 3 racks. This company in Germany, in Australia, they send us a couple of them for free, actually for fun. And we use it actually for training and processing the inference before we deploy in drones. Then here is the data that we were looking for. So we have categories, right? The CLS we mentioned, right? So the categories: altitude, position, software, speed, micro average, macro average, and a weighted average, and a sample average. So the miner that I was mentioning, it has 2 GPUs. It's a GTX GeForce RTX 3080. And then it took around total 6 epochs, around 18 minutes for training, around 11,245 data points. It's created from scratch. So it sounds small, but it's not really small. It was painful to create. And then then, if you go from the altitude, we go in altitude, we already decreasing the altitude, increasing the altitude, and all of the average. So we already have around 8,102 data points. It took around 15 minutes for training on this setup of the Bitcoin miner, or the former Bitcoin miner. Then, for the positioning, right, left, right, all of these things. So even the orbits, it took around 4.5 minutes, because the data points we have is around 2,561 data points for the whole entire things. Then this is a little bit hectic, and you can see the number is not really as we want, because we look into what about if we put on the drones Geiger-Müller tube for looking for radiation, like searching for some uranium on the ground, or like some radioactive material, and then you can have app on your phone say that this zone on this GPS coordinates avoided, there's radioactive material. And we are working with some nuclear engineer department from Purdue University about some crazy idea for having some nuclear detectors on these drones. Then, air pressures. So we just bought some very cheapy air pressures. That's why the number is not really the best. But, we are actually looking for more expensive and sophisticated one to get more accurate data. So it took around 1.5 minutes. And the data points wasn't really that much sufficient, 843. That's why the number didn't reach to the point of almost 100%, which is basically what we need to succeed in our process. Now, we are looking into the second part of the AI we have in the system, which is our eye, our further eye. So the hawk eye, we need YOLO. And YOLO. So end of the day, this is a graphical representation. By the way, this is the Jetson, this is the Turing Pi on my desk at home I was playing with. I put 4 nodes of the Jetson Orion. No, the Jetson Nano, actually. And, in the screen, you can see all of the nodes in front of me live, and all of the PMOS tracking is running, and it was really great. And even I look into the energy I was consuming, it was almost nothing. I was less than 1 watt, and that was really impressive, actually. And even, I didn't go, I went inside in every single GPU, and I put the fan up to the 128, so it could be a fixed rate, so it would be cold no matter what. I have massive or not massive processing. So if you look here in the latency, energy consumptions, and even the speed by FPS, by the frame per seconds, you will find out that, the comparison for us between the TRK1, if it's beyond all of the 4 nodes, compute module 4 or Jetson Orion NX, you will guess, the Jetson Orion will be doing the great, but then, based on the performance versus energy, you will find that TRK1 is our best option in this case. And, now I'm going to show you something which is basically Disk Pi fighting Jetson Nano doing the same job, which is basically running YOLO. Let's see. So, here is this. Here that. This experiment I done with my students at 3 a.m. and we were just having fun in the lab. And we run RabbitMQ because, end of the day, we try to play the game of the out of order versus round robins feeding the PMOS and collecting the FPS, the frame per second. So we take every single frame, tag it, and then, we make out of order, and then, make it round robins, and we start looking into which one would be the fastest and by how much. Okay, now the performance results here is not really the best because, we turned it off the fans because we want it to be in a low energy consumptions. So pretty much the heat went up, and, this is one of the possible actually thing that we are thinking about, which is adding an extra element in the Kubernetes, allowing us to play with energy. So I will monitor the energy of the battery, and then, if I see the battery is almost dying, it's like, you're running a marathon, but then, you came in the middle and you start feeling like, you cannot breathe. What you're going to do? You're going to stop or you slow down. So pretty much, we're going to slow down the heavy lifting things, fans, something, until, we can be gasping or harvesting some energy. There was actually in Los Alamos National Lab, I saw something very interesting. You know, if you bring a helicopter and you put it in high altitude, but then you stop the helicopter somewhere, then, you know, with the gravity, the blades of the helicopter will start moving, and then, you know, it start actually getting more energy. So if you start playing this game in high altitude, low altitude, without losing your balance, you can harvest some energy from the kinetic energy. But, you know, how much that will be, this is a question. It depends on the geometrical representation of the whole entire drone, which is very interesting thing that, you know, we can do further simulation for it with a bunch of drones that we have, and we can come out with a secret recipe. Then, you know, here is some drones. Let's have some fun. So, you know, this one we put it in the lab is using the EDF, but this is a crazy drone. It has joints. So every single arm, it has servo motors, and in the servo motors, it can actually flip like this, flip like that. So it can even make a VTOL, STOL, like, you know, F-35 and F-16s. F-16s is like, you know, STOL, VTOL is F-35, which is basically like the British version of the jets Harrier, which is they take it on the aircraft carrier with a short runway. So students were afraid, so, you know, there's somebody, so we got like a little foam and we were playing with it, you know, so we can actually, you know, tuning the motors, and you can see that, you know, it's flying, but it's doing like this. So that's pretty much, you know, the yaw, right? The yaw, raw, right, the pitch, right? And then, you know, let's go to the other one. The other one is more fun because we destroy it, which is cool. You know, I remember, you know, I was talking to one of the NASA folk, and we had a competition in the desert, Mojave Desert, and we were running some of this experiment, but on UGV. And he told me in the early stage before the SpaceX, he was telling his folk, break stuff as much as you can, you learn. But now because they're competitors, it's expensive. See, it's flying and doing, you know, phase shift, right? It's making H, and then it's making X and making O, but then, please. But I will tell you, it didn't really massively get broken because, you know, we use resin printers. So we use certain material with ultraviolet that it actually make mold, and it's making the whole chassis really tiny. Then, you know, when it falls, the more expensive part, it will be like a secure box, and the rest of the drone will be bye-bye. There is no drone. You're not going to see anything in the ground. Now, you know, my students having fun. He's throwing the drone in the air. He throw it and just, you know, good luck. And, you know, the other guy has the NLP in the computer, but, you know, but it's not in the video. I'll show you another video. And the drone now is flying by itself. Mission planner has its own vision and is looking for the target. It's basically, I cannot leave without finding my target. Unless my battery is almost, so I would just like land safely by looking into the location from the computer vision. So he is just going around for safety, you know, just like he's afraid somebody will get hurt. And he's just looking into some stuff in his hand, and he's just, you know, hovering in the air. Because we like parallel processing. While you're watching this, we can watch the other one. So, you know, this one, you know, there is regulation in US about, you know, drones altitude. So, you know, FAA approval, right? Everything. This one, we went beyond the limit. But then, you know, we took some approval from the Air Force. This is the campus of the university, so we play in this area in front of the College of Engineering. So we put lights because we don't hit any airplane or something, you know, because if we like helicopters and stuff like that for the police and ABD and all these things, right? Anyway, I have a bunch of videos I can share with you later. But now the Mojave Desert. So that guy, actually, we brought him from the Navy, Dr. Benishang, as my collaborator for this grant. You know, he was chatting with the drones while, you know, the drone is doing what he's doing was chatting, and, you know, has Turing Pi on the top and everything was working. We tried first to put the Turing Pi in the ground in the UGV, and then we send the information through the telemetry. And the second experiment, we say, but the telemetry, if the data is a lot, the telemetry has a bandwidth limitation. Just migrate the whole entire Turing Pi in the drones and see what will happen. So we made this experiment. But anyway, this is Mojave Desert. And this car is doing the same thing, but it removed the altitude from the training of the NLP because we didn't need altitude. The drone, it could be the next step. We're gonna make this car fly. But now it's just like driving around based on chatting and even computer vision process. And here is the car in front of you, and under the battery we put the Turing Pi chassis, and that actually it was the board in front of you there. Then this is the experiment. I made it by myself. I'm sitting there with messy t-shirt because I like him. And then, that's my students. And the drone's in front of you, and I can show you how it works. Look. So I am chatting at the moment with the drone. Just go left 100, search for the whatever. And of course, if we have a night camera and whatever, it's gonna be even more sophisticated in that case. But of course, it's gonna be more data processing. So I just say, just like, take off. And now it's just waiting for me to say, go up, go down, whatever, And actually Turing in the top. It's the one that's lighting there. And it's just like waiting for me. And, I just, whatever. It takes more time because of the trick of the round robins and the out of order. But later it will start like, taking the orders, it's start moving actually. And it was windy, so it's actually the Kalman filter and PID is compensating the movement of the wind, and it's just like landed because I said just go land because it was really windy in that time. So pretty much this is my whole team. When and this big drone is really quite interesting. This big drone, it can carry human, but what I did, it carried telescope. So do you remember in the Eclipse they give you this little mirror thing, you cannot look like this. But what about if I sit in my office and send the telescope drones, and then with my app in my phone, and then it will do all the processing for me, and it clip pictures and videos and everything, and just send it to me in the streaming, and it could be a very nice product even to be sold. And as you can see, GPT is giving me this new vision, like the Martian. You already have here YOLO, NLP, and you can be using for multiple applications at the same time. And because I'm a big fan of Leonardo da Vinci, simplicity is the ultimate sophistication. So energy, simplicity is in front of you for the setting, chatting and talking to it, and also scalability. Because at the moment the scalability, it was on the board on the drone. But what about if the drones itself is a compute node? And then all of them will be orchestrating. You can make it like a transformers. So if you actually, I have a team participating in NASA competition. It's called NASA Minds, and we built a protocol using all of this to make drone docking. So the drones will be docking in the air, and it make like an umbrella, and then they will be connected through the Ethernet cable to take the high speed, and then Kubernetes will be considered all of the nodes. So I have 4 in these drones of Jetson, and 4 here, 4 there, 4 there, 4 here, and it could be some of TRK1, some of Jetsons, and it could be a heterogeneous system in that case. And then you can just assign using Kubernetes while you're sitting in the ground. And the ground shouldn't be a human, it should be a UGV. Now, special thanks to the sponsors, the US Navy, NAC, Lockheed Martin, the NAVWAR centers in Corona, NASA Mind, Artemis mission, my library, Configured Space Computing Lab, Capoli Pomona, which is basically my school. Thank you by all different languages. Thanks for all of those guys. And any questions? Thank you.
Is there any question in the room?
I have one.
Sure.
In the test you showed with the drones, the flight controller is running on the Turing Pi, or you have a regular
I love this question.
flight controller?
I love it. Basically, we did both. Because the flight control, I will tell you something even more crazy. I have a student, a supervisor from Switzerland. He sent him to me, and we came into the point which is really quite interesting. In the quadcopter, You already have ESC, which embedded system, electronic system speed controller. It has a microcontroller, which is the digital part of the game, and a network of the MOSFET, which is the analog part, because you are dealing with the 3 phases of the brushless motors, right? But this is expensive because you already have 4 microcontrollers. So what is the best practice here? We remove all of those microcontrollers and we make a PMOD on the pink board, and we made the pink board as one ESC. And that lowered the energy and extended the drones to be flying for almost 45 minutes extra. And adding one of the nodes, as you mentioned, one of the PE of the Jetsons, is going to make it even fly for almost 3 hours extra. This is the trick. And, it's really quite interesting. Yes.
Yeah, one other question, like regarding the bird. So I'm just like trying to understand. So you have the bird and like you fine tune by removing the last layer to output the coordination. Yeah.
We add the extra 2 layers by the end of the bird,
Yeah,
the
so
pre-training.
yeah,
so we keep everything just the 2 layers for the elimination.
Like you're fine tuning like for the target.
Yes.
So my question is, your prompt has like defined list or is it open?
It's open.
It's open. So how you can like ensure that this prompt will lead to the same coordination? It's an open problem, yeah.
It is an open problem. Yes, I agree with you. I make it open because we're still investigating. Because our idea is actually to run this year Llama. We Bird it was the first year. This year gonna be Llama. So we're gonna play with a bunch of different versions of Llama, and Llama's a lot of actually parameters. So pretty much we need to test GPUs in this case. And in the early, when I said cloud and edge, we are not actually eliminating the cloud, but we need to have a cooperative edge cloud work, right? So that's why we are moving to Llama in this case. So of course it's open, yes, and yes, I agree with you.
No questions? Anyone online has a question? Just unmute or type it in the chat, please. On that. So anything else here? So I guess we're right on the top of the hour and we have to leave the meeting room. Thank you again, speaker. Thank you everyone for joining us. Thank you.
Oh, somebody else. Where is this technology most likely to be used? Army. Could be used in Army, and it could be used also for it's Army. It's Army and security, and also could be used for the firefighters. It could be used even with healthcare systems, right? I remember when I was a PhD student in Norway, the news said that the Royal Norwegian Army sent F-16 to one of the really far city because one of the patient has almost heart attack, and it was the only way for them is to transfer the device for this electric shocks, right, by using F-16. So if I use my technology, I don't need to fuel F-16s in this case, right? So it will be cheaper because fueling F-16s is a big mess, and you need a runway because it's tall. Yeah, it's a lot of stuff.
Thank you. Any last questions?
One question.
Yes.
Regarding to that other question, if you're going to switch to Llama, how are you foreseeing the energy requirements changing, going up?
I'm gonna tell you something crazy. These drones will not be using any more LiPo batteries. It will be using fuels. I got some of turbine engine from Germany, from a company called JetCat. So instead of the propellers, it's gonna be each side is gonna be a turbine engine. And then, there will be a fuel tank in the middle. And even we're going to allow hosts to come from other drones to even fuel the drones, like the Air Force docking for the refuel. So in that case, I'm no longer afraid about the LiPo battery. Then Llama, good luck, Llama. So what?
Solar energy is not viable in this kind of devices because of the size, maybe of the panels.
Then we're going to have a cloud computing in that part. We're going to have a cloud and we're going to be edge computing together. So instead of just like solo edge computing, it's going to be a kind of negotiation about, which one in which part is going to be a cloud, which part is going to be an edge.
One last question, like regarding the Kubernetes.
Sure.
It was like it was like easier like for you to address the container or the pods running directly to the GPUs of the Jetson?
Yes, there's some flags you have to turn it on because the default is CPU. Then you have to do some process. Then it will be processing with processing elements. Yes, I agree with you. It took me 3 months.
I think I'll redo Sarah's question because I
you didn't. I didn't
I'm
express
sorry.
myself correctly.
solar power instead of fuel.
Oh, solar power, I will tell her. We are building a drone actually with solar power. No, but the problem is the how to say, you need to have a very, very, very lengthy, long wings, and it's better to make it fixed wing. So MIT already built a huge, gigantic fixed wing airplane. It could be flying for almost 24 hours, but then it's not at quadcopters.
No, but if you can refuel from while flying, you could also kind of.
No, but the problem, if you play a game of electricity, you're gonna be hit by the limitation of physics, which is basically the charging rate based on the capacitance and resistance.
Okay, that I don't know.
That's for sure, because I'm a hardware person. So end of the day, that look at the crystal, which is running the clock, right? So it's a bunch of RC, they call it RC circuits. You charge, discharge, 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 and then you refine it. It look like a square. So the charging and discharging is already tied by something that's called time constant. This time constant is going to be a troublemaker because while you're refueling with energy, you might actually lose the whole entire drones. And while it's actually while you're connected, you're going to lose the other one. And don't forget, the drone itself is not important. More important is the data, because this is our golden egg. So end of the day, you sabotage the whole nothing. So.
But in this situation, if it's going to be problematic when you feed directly the energy solar to CPU directly, but there is battery in the middle.
Then you can have a super capacitor. If you have a super capacitor in the middle to transition between solar from the other drone until you will go down, then that will be the best. It's a little bit tricky in electronic side, but it could be a doable. Actually, it's really, really doable. But in that case, you're gonna have a kind of heterogeneous. It's no longer fixed wing or just quad. It's gonna be both together.
This is the last question.
Oh, will it work with neuromorphic sensors camera? Oh, I would love to try that. The problem, I don't have it. So if I have one, I would love that. We like to push the boundaries.
Okay. Yeah, I think we're done. Thank you. Thank you, everyone. Thank you.
Just think.
So stop the recording.